Hello friends, Mr. Burrell here. We're in the middle of our unit on right triangle trigonometry. We started off talking about the Pythagorean theorem and labeling sides of a right triangle as opposite, adjacent, and hypotenuse. We've talked about sine, cosine, and tangent. Hopefully you're starting to become a little bit familiar with this mnemonic here to remember sine, cosine, and tangent. And in this last lesson, we also talked about how we would find missing sides in a right triangle, how we would solve for a missing side using sine, cosine, and tangent, some of these right triangle trigonometry principles. Now we're going to go on and talk about how we can find missing angles with trigonometric ratios, so like sine, cosine, and tangent. So by the end of this lesson, these are the things that I want you to be able to do. I want you to use the properties of sine, cosine, and tangent to solve for missing missing angles. I don't know why that says side. For missing angles in a right triangle. Okay, that's the main goal. Yesterday we wanted to find missing sides. Today we want to find missing angles. So take a second and look at these problems. In each of these problems, I want you to solve for the variable. So solve for x here, solve for y here, solve for y or for z here. Think about what specific steps you need to take to solve for x, y, or z, and y. So for example, in this first one, I have x plus 5 equals 17. How do I undo plus 5? I subtract 5. Because addition and subtraction, they're opposites of each other. They undo each other, right? So I'd end up with x equals 12. What would I do here with 4y equals 32? Well, if 4 is being multiplied by y, I'd have to divide by 4 on both sides. That would give me y equals 8, right? Why did I divide by 4? Because multiplication and division are like opposites of each other. They undo each other, okay? What about z squared equals 121? How do I undo squaring something? Well, I square root that something. Why do I do that? Because squaring and square rooting are opposites of each other. They undo each other, okay? And the square root of 121, I think, is 11. So we went through those specific steps to solve for x because those operations undid the operations that were being done on x. I subtracted 5 because x was being added to 5. I divided by 4 because y was being multiplied by 4. I square rooted the z squared because z was being squared, okay? Now, take a look at this. So this could have been similar to a problem on our homework from the other day, but I have this angle here. Angle, remember, this is pronounced theta. So real quickly, as I have been doing with right triangles, help me label the sides. So if this is the angle I'm looking at, this would be opposite, adjacent, and hypotenuse. Okay. Now let's write a trig function based on this angle here. Well, it looks like I have the opposite and adjacent sides. So thinking back to SOHCAHTOA, which trig function is going to use the opposite and adjacent sides? The tangent. So tangent of theta, this angle here, is equal to 8 over 5. Opposite over adjacent. So the difference between this problem and one we would have done last time is this time I'm missing an angle. So the instructions to this problem might be like solve for the missing angle or something. But how do I do that? How do I solve for this angle? I'm taking the tangent of that angle. Over on these problems, I undid addition with subtraction, I undid multiplication with division, I undid squaring with square rooting. How do I undo tangent? I'm taking the tangent of theta. How do I undo tangent? Well, lucky for us, there's a way to do that. So, in examples like this, sine of theta equals 1/2, cosine of theta equals 4/5, tangent of theta equals 1. In each of these cases, how do I solve for theta? How do I undo sine, cosine, and tangent? Well, the way that I undo sine is with the inverse sine. So like before on this problem right here, I subtracted 5 on both sides. To get rid of the sine here, I'm going to take the inverse sine on both sides. And you'll note in your calculator, if you take a look at your calculator, whether you're using one of mine or if you're using somewhere else, right above the sine button, there's a little like sine -1. See that? Mine is backwards. But in blue, it says sine with like a little -1 above it. That's the inverse sine button. So if you push on my calculator the second button, or the blue button, and then you push sine, it pops up with this little sign of -1. Sine to the -1. That's the inverse sine. So if I take inverse sine of 1 divided by 2, 1/2, for example, I get 30. Here, in order to undo cosine, I do the inverse cosine, which is, in my calculator, the second cosine button with this little -1. And when I do the inverse cosine of 4 divided by 5, closing my parentheses, I get like 36.87 degrees. That would be my angle. And I undo the tangent by taking the inverse tangent. So the inverse tangent of 1 ends up giving me like 45 degrees. So I undo sine, cosine, and tangent if I'm taking the sine or cosine or tangent of an angle and I'm trying to solve for that angle. I need to use the inverse of those trig functions. Inverse sine, inverse cosine, and inverse tangent. So let's test that theory real quick. I have this triangle. I have all the angles and sides labeled. So looking at my triangle here, let me label my sides. If I'm looking at the 30-degree angle here, here's my 30-degree angle. Let me color it all in there. This is my hypotenuse. This is my opposite side. This is my adjacent side. What is sine of 30? Well, this angle 30 degrees, sine of 30 is opposite over hypotenuse, or 1/2. Now, in my calculator, let me go ahead and type the inverse sine of 1/2. We kind of did that on the previous slide, but the inverse sine of 1/2 is 30. So if I'm given the angle, the sine of that angle, 30 degrees, will give me the opposite over the hypotenuse side, whatever that fraction is. But if I know the fraction, instead, if I know the decimal, fraction of the decimal, then if I take the inverse sine, it will tell me what that angle is. Okay? Let's test this out. Let's do something real quick. So we pulled up this little applet the other day. Oh gosh, I think that's gonna work. Let's see if it'll pull up from here. Okay, well, it looks like that's not gonna work. But you kind of see what's going on. If I'm given an angle, my calculator will tell me what that ratio is, what that fraction or decimal is. If I'm given what that fraction or decimal is, what the sine value is, if I take the inverse sine, it will tell me what the angle is. Okay? So for example, in your calculator, go ahead, we did this one already. So go ahead and type this in your calculator. Type cosine of 90 degrees. And I'm going to go ahead and pull up Desmos so you can see. Let's see here. I'm going to go ahead and type in cosine of 90 degrees. It gives me, let me make sure I'm in degrees. It gives me 0. The cosine of 90 degrees is 0. Okay? Now, let's see if I take the inverse cosine of 0, I get 90 degrees. Cosine of 90 degrees is 0. The inverse cosine of 0 is 90 degrees. Let's do the tangent of 45, shall we? What happens if I do the tangent of 45? That's equal to 1. What happens if I do the inverse tangent of 1? I get 45 degrees. That's really cool. If I'm given an angle, my calculator will tell me what the sine, cosine, and tangent values are. But if I give you the sine, cosine, and tangent values, my calculator can also give me the angles. So just as a general rule, with these types of problems that we're going to see, I use the Pythagorean theorem if I already know two of the sides of a right triangle, and I'm trying to find the other side. I use sine, cosine, and tangent if I'm given one side and one angle, and I need to find another side. If I'm trying to find another side, and I'm given one side and an angle, I use sine, cosine, and tangent. I use the inverse trig function, so the inverse sine, cosine, and tangent, if I'm given two of the sides, and I need to find an angle. Okay? Let's practice some of these. So for example, let's look at question number 1. I have this angle right down here. I called it x here. You can call it whatever you want. If I label the sides, this is hypotenuse, opposite, and adjacent. Okay. Well, which trig function am I going to use? Sine, cosine, or tangent? If I look at my SOHCAHTOA, which trig function am I going to use? Well, it looks like here I have the opposite side and the adjacent side. Well, opposite and adjacent, that's going to be tangent. So tangent of x, because I don't know what this angle is, tangent of the angle is equal to opposite over adjacent, or 4 over 8. Well, in order to solve for x, to solve for this angle and undo tangent, I need to do the inverse tangent, so this little tangent with the -1 of 4 over 8. So in my calculator, I'm going to push the second button and then tangent to get that little inverse tangent of 4 divided by 8, and that gives me 26.57-ish degrees. About between 26 and 27 degrees. Okay? And that's it. I'm done. I've found my missing angle. Yeah. Let's do one more of these kind. So if I'm looking at this angle right here, hypotenuse, opposite, adjacent, which trig function am I going to use? Well, I have the opposite and adjacent sides, which means I'm using tangent again. So tangent of x is equal to opposite over adjacent, or 2 over 1. So to solve for x, I'm going to have to undo tangent with the inverse tangent of 2 over 1. So in my calculator, I'm going to push second tangent, 2 divided by 1, close parentheses. And I get x equals 63.43 degrees. About 63 degrees is how big that angle is. These triangles aren't drawn really good to scale, but you kind of get the idea. So what if I give you something like this? It says, find each angle measured to the nearest degree. I don't have any triangles, but I do tell you that sine of y is equal to 0.766, tangent of w is equal to 1, cosine of v is equal to 0.7314. So in order to solve for y, w, and v, in each of these cases, I'm going to have to take the inverse sine of 0.766, the inverse tangent of 1, and the inverse cosine of 0.7314. So if I push second sine 0.766 in my calculator, I get about 50 degrees. If I take the inverse tangent of 1 in my calculator, I get about 45 degrees. And if I take the inverse cosine of 0.7314, I get about 43 degrees. So if I give you something like this, sine of a variable, sine of an angle equals something, either a decimal or a fraction, I use the inverse sine, cosine, and tangent to find that missing angle. Let's do one more with a triangle. So say I'm looking at this angle right here. Let me label this side as opposite, hypotenuse, adjacent. Let me write SOHCAHTOA up here at the top so we can remember what we're dealing with. So which trig function am I going to use if I have my opposite and hypotenuse sides here? Well, opposite and hypotenuse sides, that's going to be sine. So sine of angle x is equal to opposite over hypotenuse, or 5 over 7. Then, in order to find my missing angle, I need to take the inverse sine. To undo sine, I'm going to use the inverse sine of 5 over 7. And in my calculator, if I take the second button and then sine, it pops up that sine of -1 of 5 divided by 7, close parentheses. I get my missing angle to be 45.58 degrees. Really close to a 45-degree angle. Okay? So that's what we're doing. We're using the inverse trig functions to solve for missing angles. Okay, So I want you to pretend something. I'm going to pretend that we have the shortest person in our class and the tallest person in our class standing across from each other. So say I have Shorty over here. Call him Bob. He's fine with being short. It's okay. And say we have this really tall fella. Call him Joe. He really likes being tall as well. And say they're standing 5 feet apart. And let's see. Let's say Bob is like 5 feet 2 inches tall. And let's say Joe is 6 foot 2 inches tall. Okay? So what I've done is I've kind of created this little triangle between Joe's line of sight and Bob's line of sight. See how Bob has to like look up at Joe in order to see into his eyes because Joe's so much taller? So Bob has to, instead of looking level, see this? Instead of Bob looking level, he has to look up at a certain angle in order to get to Joe. He has to crane his neck to look up into Joe's eyes, right? So what I want us to do is determine at what angle does Bob have to crane his neck up to look Joe in the eyes, okay? So if they're standing 5 feet apart, that's equivalent to 60 inches apart, okay? And then let's see, how much taller is Joe than Bob? If Joe is 6 feet 2 inches tall and Bob is 5 foot 2 inches tall, it seems like Joe is exactly a foot taller than Bob, or 12 inches. So Joe is 12 inches taller than Bob. So this little side of this triangle would be 12 inches. And this is the angle I'm trying to find. How high, or how much Bob has to crane his neck to look at Joe, okay? All right, well, let me label the sides of this right triangle because I've formed this little right triangle here. So here's my hypotenuse, here's my opposite, here's my adjacent. So thinking back to SOHCAHTOA, what trig function am I going to have to use in order to solve this problem? Well, I have the opposite side, I have the adjacent side. That's going to be tangent. So tangent of this angle, theta, is equal to opposite over adjacent. 12 inches over 60 inches. Okay? So in order to find the angle, I'm going to have to take the inverse tangent of 12 over 60. So in my calculator, I'm going to take the inverse tangent of 12 over 60, which gives me an angle of 11.3 degrees. So, Bob, you have to raise your head at an angle of about 11 degrees in order to look Joe in the eyes. Pretty cool. I think that's kind of a quirky, kind of fun, real-world example of where we can use trigonometry to solve for missing angles. And that's it. That is all I have for you today. Hopefully by the end of this lesson, you now feel a little bit more comfortable using properties of sine, cosine, and tangent to solve for missing angles in a right triangle. I'm going to fix that typo, don't you worry. So I hope that was helpful. Please don't hesitate to reach out to me if you have any questions whatsoever. And I hope that you enjoyed that as much as I did.